Hello students. Today's session is magnetic properties of transition elements. Okay. In general, the magnetic property why is come to the material. Okay. So why the magnetic properties come to the material? Now I will discuss it. Okay. The magnetic property is more related with the electronic configuration. So the magnetic properties depends on the elements. Okay, so it is depends on the magnetic properties depends on the electronic configuration. So the magnetic properties depends on the elements of the electronic configuration. Okay. In an atom, electrons revolves around the nucleus. Okay. At the same time, it's a spin on a same axis. So the electrons having the two types of the movements. One is the spinning motions, and second one is the orbital motion. Okay, spinning motions, and another is the orbital motions. These two movements create the small magnetic moments because the electrons are charged particles. So the charged particles revolves itself and also revolves around the nucleus. So the charged particles revolves itself. Okay, revolves around itself and also it revolves around the nucleus. Okay, so only the magnetic power is created. So that is measured like a magnetic moment. Okay, it is measured like a magnetic moment. It is based on the magnetic properties. This can be classified into diamagnetic, paramagnetic and ferromagnetic. The diamagnetic, paramagnetic, then third one is the ferromagnetic, and the fourth one is the antiferromagnetic. Fourth one is the antiferromagnetic. Okay. Now the first one is diamagnetic. So why it's come? It is actually the diamagnetic means it will not having a magnetic property. It will not having a magnetic property. That material is called a diamagnetic substance. Why? If the substance have a magnetic property, the condition that having a unpaired electrons. The conditions it is conditions is that having a unpaired electrons. Okay. Its condition is it should contain the unpaired electrons at least one. So the diamagnetic electrons not having a unpaired electrons, so it's having a paired electrons. It's having a paired electrons. Okay, so the electrons are paired means does not have a magnetism. Paired means it does not have a magnetism because the paired electrons like it likewise. Okay, like it is the two electrons likewise up and down likewise. So two electrons having a equals and opposite spin, equal or opposite spin. So electron rotate then create the magnetic property is nullified by the magnetic paired electrons with it. So the net, okay, it's nullified because it is a spin. It's a equal and our opposite spin only magnetic is there. So net magnetic moment is a 0. Net magnetic moment is a 0. Net magnetic moment, therefore the net magnetic moment is 0. Therefore 0. So therefore the repelled external magnetic field. So the paired electrons will not exhibit the magnetic property. Will not exhibit. Second thing, it is a paramagnetism. Second thing, the paramagnetism. Okay, it means it becomes the magnetic property. It behaves in the paramagnetic means it behaves the magnetic property. So there will be the attracted by the external magnetic field. Okay, so the transition elements of N. Okay, the transition elements of n minus 1d is having a unpaired electrons. It's having a unpaired electrons. So the total magnetic moment is equal to the spin. The total magnetic moment is equal to the spin angular momentum. Okay, so the electrons are around the nucleus, the unpaired electrons are around the nucleus. So the total magnetic moment is equal to it is equal to, that is a spin motion and also the orbital motion is there. So it is the total magnetic moment is equal to spin angular momentum and orbital angular momentum. The spin angular momentum or orbital angular momentum. In 3D series, the orbital angular momentum is very less. Okay, this very less means the magnetic moment in a 3D series is a 3D series is one spin only magnetic momentum. So the orbital angular momentum is very less, means it's neglected. So only you take the it's neglected, so only you take the spin only angular momentum. Spin only angular momentum. So the 3D series is the spin only magnetic momentum. Okay, so it's the electron's rotation is revolved around the nucleus like the electrons flow on the closed circuit. So it's behave as the tiny magnet. So the spin only magnetic moment is given. Okay, the spin only magnetic moment is get it. So that spin only the magnetic moment, it's behave like a closed, the electrons flow on the closed circuit. So the spin only magnetic momentum is given by, okay, spin only magnetic momentum is given by the one of the formula. The spin only magnetic moment is given by the one of the formula mu s is equal to square root of n into n plus 2 mu b, or it is called the Bohr magneton. Okay, so the material exhibit paramagnetic electrons that behaves as the electrons dipole. So the materials exhibit paramagnetic, the electrons behaves as the electron dipole means, but they are separated it. So that dipole electron is that separated it. And also it's randomly arranged it. So in the normal conditions, it will not be not a magnetic moment because the dipoles are randomly arranged. But when they apply the external magnetic field, the random of the dipoles are aligned parallel to the applied magnetic field. And hence they are attracted by the external magnetic field. In the normal conditions, they are randomly arranged, so it's not behave a magnetic moment. So when we apply the external magnetic field, it is attracted by the external magnetic field. Then the randomly arranged electrons are aligned, and after this parallel to the applied magnetic field, and also hence they are attracted by the external magnetic field. Okay. And next the ferromagnetic, some of the it is a ferromagnetic means it is a permanent magnetic behavior. Some of the elements exhibit the ferromagnetic property, that is a iron, cobalt, nickel. Okay, so that ferro is the same as the paramagnetic. The one is different, that is both the having the unpaired, okay, one is different, that is both having the unpaired electrons, but the paramagnetic is a dipole is randomly arrangement. When the applied external magnetic field, it's surrounded like a orderly alignment. But the ferromagnetism, already the dipole alignment is orderly arranged, so they are called a permanent magnetic field. Okay, it's a next is the antiferromagnetic magnetism. It is similar to the diamagnetism. There will be the repelled by external magnetic fields. They will not exhibit the magnetic property. Okay. So the next come to the transition elements. That is example 3D series. Okay. That is scandium to zinc. So the scandium to zinc, number of unpaired electrons and increased in the period, they again their number of unpaired electrons are decreases. Okay. The magnetic moment also increased. The first scandium to middle, then the middle to zinc, they are decreased. So when the number of electrons increases, the magnetic moment also increases. Okay. So number of electrons are increases means when the number of electrons are increases, the magnetic moment also increases. Okay. Then the number of the mu s is equal to unpaired electrons. N is equal to it's number of unpaired electrons. So N denoted the number of unpaired electrons. So number of unpaired electrons in the transition elements, how they are. Number of electrons mu s is equal to square root of n into n plus 2. So n is equal to number of unpaired electrons. Okay. Number of how they are see some examples. Okay, how they are arranged in the transition elements. See some examples. First thing, you memory this scandium to zinc. Already I told in that 11th standard, told you. 11th standard, I already explained that the scandium to zinc outermost electronic configurations I written on the board in your previous classes. I think your memory it. Suppose you are not memory means you have to memory that your memory must, because this lesson are also that the next lessons you have to use that outermost electronic configurations of the 3D series scandium to zinc. Okay. That is so we will write the outermost electronic configurations of this scandium to zinc. Okay. Scandium to zinc. Okay. You just memory it, the outermost electronic configurations. Okay. You remember it. These after then only it is very easy to solve that. And also coordination chemistry also used these outermost electronic configurations of scandium to zinc. Coordination chemistry, so you have watched it. Okay, now the scandium 3 plus zinc 3 plus copper plus the magnetic moment is mu is equal to 0. Magnetic moment mu is equal to 0 because this is not having unpaired electrons. Okay, because it's not having unpaired electrons. Watched it. The scandium electronic configuration is 3d1 4s2. Okay, so scandium 3 plus means you remove the 3 electrons, means not electrons is there, so that scandium 3 plus is equal to 0. Next, zinc 2 plus means the 3d10 4s2 is a zinc, and you have to write it remove the 2 electrons, so 3d10, and also copper 3d10 4s1, remove that 1 electron. Copper plus means remove the 1 electron, so it's get the 3d10 only. So both of the having no unpaired electrons, they are paired, so n is equal to 0, isn't it? So n is equal to 0 means you applied in that equation mu is equal to square root of n into n plus 2. So what do you get? Mu is equal to 0. So no magnetic moment. Okay, so these ions are said to be diamagnetic. The calculated value is more or less near to the experimental value. Okay, the magnetic moment in these elements, and the scandium 3 plus is not having electrons. Already you watched it. Scandium 3 plus already you watched it. It is not having electrons. Only 3d 0. Next things. Okay, 3d 0. Scandium is not having electrons. And the next thing, the titanium. Titanium is 3d2 4s2. Okay, so titanium 3 plus. Titanium 3 plus is equal to 3d1, and also vanadium 4 plus is a 3d1. Vanadium 4 plus also 3d1, And also vanadium 4 plus also is having a 3d1. Vanadium 3, titanium 3 plus and vanadium 4 plus is having a 3d1, so no unpaired electrons. So is substituted in the formula. N is equal to 1 electron, only one unpaired electron is there. Okay, 3d1. Only one unpaired electron in the titanium 3 plus. And the next vanadium, you substitute in the equations n into n plus 2. So 1 into 1 plus 2. So you get the root 3. The answer is 1.732 Bohr magneton. And then D2 configurations, explained it. Okay, D2 configurations means titanium 2 plus. Titanium 2 plus. Titanium 2 plus 3d2 4s2 means removal of the 2 electrons. Only the titanium 2 plus means 3d2 only it. And also the vanadium 3 plus also, so only 2 electron in the titanium 2 plus. And then substitute in the equations 2 into 2 plus 2. So what is the answer? Square root of 8. So that answer is 2.83 Bohr magneton. Okay, and next a D3 configuration. D3 configuration, so that the 1.732 is it is absorbed value is 1.75, the 2.83 is absorbed value is 2.86, 2.86. Okay, next the D3 configurations. Example, chromium 3 plus, manganese 4 plus and vanadium 2 plus. Okay, all those having a 3d3, only the outermost electron is having a 3d3. Okay, because removal of the electrons from 3 electrons from chromium, 4 electrons from manganese and 2 electrons from vanadium. Okay, and the number of unpaired electrons, how many is that? 3 unpaired electrons in that chromium 3 plus. Okay, substituted in that the equation. So square root of 3 into 3 plus 2, so root 15. The answer is 3.87. The absorbed value is 3.86. Okay, the absorbed value is 3.86. Okay, thank you students. You will watch it, D4 and D5 configurations. You will follow it, you will do it. Thank you.